morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to discuss a topic related to time domain analysis. Basically, time domain analysis is of two parts. One is transient system analysis, and second one is steady state response analysis. Under that, there are basically points. First one is first order system and second order system. Let us see one by one. So basically, why we are going to study these two topics. At the end of this lecture, basically the student should able to learn and identify between the transient response and what is steady state response. Also, to obtain the transient transfer function for the first order system based on the graph analysis, means signal flow graph we discussed in the previous lecture. Also, the reduction of the block diagram system from the system. Also, to obtain the familiar with the wide range of the responses for the second order system. Let us see one by one. So basically, these are the type of the transient system. So what you are expected to learn? See here, first order system, second order system, then Root-Hurwitz criteria, and steady state error. So what is the main difference between first order system and second order system, and how these two belongs to derive the Root-Hurwitz criteria to get the steady state error, transient state error, and stability of the system. See about the introduction. The time response of the control system basically consists of two parts. One is transient response from initial state to final state, and to control or to purpose of the control system to provide it a desired response. Secondly, a steady state response, the manner in which the system output behaves as T. T means time domain analysis, which approaches to the infinity. Whenever we put the time domain analysis value is equals to 0, means T is equal to 0, it should give the value of the system to be infinite, and hence the system is called as steady state response. Also, the error after the transient response has decayed, means we are going to neglect such type of the error and leaving only the continuous response. See this graph. Basically, this graph will introduce some point, means starting from value 0.1 C, that is final value of the transient system, to the maximum value of the transient system. So basically, this classical approaches to the transient analysis. This transient analysis, or just a transient of the electrical circuit, is important as steady state analysis. When this transient occurs, the current and voltage in some part of the circuit may many times exceeds those that exceed in the normal behavior and may destroy the circuit equipment in its proper operation. We may distinguish the transient behavior of an electrical circuit from its steady state, and in that during the transient all the quantities such as current, voltage, power, and energy are changed in time, while in steady state they remain invariant, that is constant in DC operation or periodical, having constant amplitude and phase angle. See here, for the initial value, that is from TR, it is moving linearly up to C max, means there is no any fundamental, that is input is going linearly with respect to time. But whenever this value reaches to the final system, it starts decreasing in a proper manner towards the time T, means whenever the feedback is given to the system, whenever there is feedback system, it will try to approach us towards the infinity value, and this infinity value will be considered as a steady state value. Okay, whenever we are going to neglect this steady state value, we get a complete value of the transient system, and this transient system will be considered as a continuous value of the system. Now we are moving towards the performance of the control system. Okay, the changes of the current voltage etc. during the transient are not instantaneous and take some time, even though they are extremely fast with a duration of miscellaneous or even microseconds. Their very fast changes, however, cannot be instantaneous or abstract since the transient process are attained by the interchange of the energy. So these are some specifications, that is max OS, then setting time, then rise time and peak time. As for the previous diagram we discussed, setting time means the value from the initial, that is a linearly moving graph is showing the setting time. Whenever it reaches to the maximum value, it is known as the rise time, and when it starts from decreasing from last point to the continuous value assisting, then it is called as peak time. There are some standard input signal basically used in this design, that is actual signal, and it is unknown. Whenever we are providing a linear value of the system, that is transient analysis, whenever we are going to find these values are unknown at the initial states. Okay, so transient response and steady state response can be calculated by taking one of the graph of input of the system to the output of the system. This is first order system we are going to study. Let us consider one block diagram, that is R of S and C of S. In this diagram, R of S is given as the input and C of S is given as the output. In between them, one error detector will be provided, that is E of S. So the test signal is the step function, that is R of S is equals to 1 by S, as error signal is given as E of S. In this first order system, a first order system without zeros means denominator, in denominator tau s plus 1. So what is the value of the system? Yes, here the pole value of the pole is -1, and here there is a no term of s present in the given equation, that is only 1 is present, so the value of the zeros is completely zero, and it can be represented by the following transfer function, that is C of s upon R of s is equals to 1 upon tau s plus 1. Means given a step input, that is R of s is equals to 1 upon s, then the system output is called as step response, and in this case it is denoted as C of s is equal to 1 upon tau s plus 1, or R of s is equals to 1 upon s in bracket tau s plus 1, and again it is equals to 1 upon s minus 1 upon s plus tau s. By taking the inverse Laplace of the above equation or above transformation, we have C of t is equals to 1 minus e to the power minus t upon tau. Now we are going to calculate this time constant. If t is equals to tau, so the step response is given as C of tau is equals to 1 minus 0.37 is equals to 0.63. So 1 is constant, it is unity, and the value of e to the power minus t upon tau is 0.37. So C of t will be obtained as 0.63. This tau is referred as a time constant of the response. Whatever the response is, transient response or time domain response. In the other word, the time constant is the time it takes for the step response to rise up to 63% of its final value. And because of this, the time constant is used to measure how fast a system can respond. The time constant has a unit of the second. See this graph. Here the plot of C of t versus time is given. Here C of t is given and time is given on the x-axis. Means by taking a step of t is equals to tau, let us plot a graph of 0.63k with respect to t is equals to tau. It is very less as compared to the constant value k, and this k will be represented as 1. So the value of 1 minus 0.63 will indicate the value of 0.37. This is an example. The following figure gives an measurement of the step response of the first order system, and hence we have to find the transfer function of the system. So the time rise time, that is symbol TR using S, is defined as the time taken for the step response
to go from 10% to 90% of its final value. So it is TR is equals to 2.31 tau minus 0.11 tau is equals to 2.2 tau. Thank you.